So in this video, I'd like to go over something called the Hamilton equations of motion. So this is called the Hamilton equations of motion. Now, to understand Hamilton equations of motion, we're going to extend our understanding of Lagrange equations of motion, but we're going to start looking at the symmetries, missing variables, specifically cyclic variables in the Lagrangian. So if you remember the Lagrange equations thus far, right, we've discussed the Lagrange and we spent a lot of time discussing it. So Q at A is a generalized coordinate. So this is the Lagrange equations of motion. And specifically, L is the kinetic energy T minus the potential energy. Now, we know from earlier, right, that symmetry operations such as missing variables are cyclic variables in the Lagrangian. So let me do an example to make sure you understand. Missing variables lead to a conservation principle. So we're going to extend that idea, and that leads us into the Hamilton equations of motion. So imagine that somebody gave you a Lagrangian. I'll make it up. Here's a Lagrangian with, I'll make these symbols. X squared plus y squared. So y dot squared. So we're looking at two generalized coordinates, x and y. And let's say this is 3x squared. So if you look at the Lagrangian, right, we have, it is a function of two generalized variables, x and y, and we notice that there's a missing variable y in this equation. Since there's a missing y, so if you can remember that the derivative of t with respect to L, the second equation, which is y dot minus partial of L with respect to y, is equal to 0. But this term is 0 because it's a missing y. So this is a cyclic variable. So the cyclic variable means that whatever this is, right, it's a constant. So the derivative of something is equal to 0. And so the partial of L with respect to y dot is some constant, a number. So this is conserved. So we have some kind of a conservation principle. So the idea is that if you're missing one of the generalized coordinates, we get a conservation principle. So let's just write this down to make sure we understand this. So missing generalized coordinate, which is referred to as a cyclic variable. So the existence of a cyclic variable leads to a conservation. So if you're missing a generalized coordinate, now what I want to get to, right, is that, so we know that from this Lagrangian, right, this partial of L with respect to y dot, meaning that 2y dot is equal to a constant. So I could divide by 2 and you could say y dot is a constant, but it doesn't really matter. What you're saying is that whatever this equation is, right, it's conserved during the motion. It's not changing over time. It doesn't change over time. So whatever this expression is, the derivative of y, which is, if x and y were actually just orthogonal coordinate system in a Cartesian plane, right, so you're saying y dot, the vertical velocity, is actually a constant. So we get a conservation. So missing generalized coordinate, the existence of a cyclic variable means that there is a conservation principle, which namely the partial of L with respect to y dot, or the generalized coordinate dot, the derivative in time, is a constant. So that's great. But now I want to get to a concept of taking this equation, right, and then extending it, right, and saying what exactly happens, right? We've looked at Lagrangian, and if you remember the Lagrangian, it consisted of variables in, let me write it out. So your Lagrangian, right, is a function of generalized coordinates and the time derivatives of those coordinates and time. So the idea is that if we're missing a coordinate, for example, let's say QA is missing, which means a cyclic coordinate, or a cyclic variable if you want to call it. This means that we have that the partial of L with respect to QA dot is a constant. So we have some kind of a conservation principle coming out of this. You have to remember that these ideas of conservation principles are missing coordinates, right? It leads to symmetry operations, which eventually leads into more advanced topics in quantum field theory, which, anyway. So all the conservation principles, right, are looking at symmetries in Lagrangian. This is Noether's theorem. Emma Noether's ideas of symmetries in Lagrangian. But anyway, so now the question is, what if there's no time? So if you have a Lagrangian that's missing a t in the expression, right, is something being conserved? And that leads us into the ideas of Hamilton's equations of motion. So let's go and try to analyze this in a little more detail. So remember, the idea is that this is 0 in a cyclic coordinate. And so we're left with that the partial of L with respect to the time derivative of that coordinate, right, is some constant. So we get a conservation principle because this term is missing. This is 0 because if Q at A is a generalized coordinate, cyclic variable. So what could we do? And the idea is, let's take a look at these equations. We know that these equations, right, there's n different equations corresponding to Q1. So the Lagrange equation of motion corresponds to n different coordinates. So we're expecting the equation for Q1, Q2, Q3, all the way up to Qn. So there are n of these equations. Actually, I don't want to write this over again. So there are n such equations over and over again. So I'd like to extend this idea, right, and see if we can extend this a little bit further in calculating something in terms of time. And the idea is that I'm going to multiply this equation, right, by Q dot A. So I'm going to take QA and I'm going to multiply both sides by this equation, Q dot A. Okay, and then I'm going to sum over all of the variables A taken from 1 to n. There. So actually I used a lowercase, so let's keep it lowercase n. So remember, so I've taken the 8th generalized coordinate, taken the time derivative, multiplied by A, and expanded it out. So let's expand this out. So we should get a summation A is equal to 1 to n of QA dot derivative with respect to time of the partial of Q at dot A minus, and I'll put the summation over here, A is equal to 1 to n of Q dot A partial of L with respect to Q at A, and that's all equal to 0. So remember, when I take the sum on both sides, right, there's a 0 on that side, so it's all equal to each other. This expression right here, I'm going to take the derivative of this product. So this is f times the derivative g. I'm going to break it apart into the summation of A is equal to 1 to n of the full derivative of Q at A dot partial of L with respect to Q at A dot. And I'm going to put the summation on this side too, so it's minus A taken from 1 to n, and the derivative of this would be QA double dot of the partial of L with respect to QA dot minus And I guess I'll leave that alone. So it's a long equation. Well, it's not so long. It's actually pretty silly. Actually, so we're now taking the derivative of this gives me this minus this term here, right? So I took, I hope you understood that. So the derivative of the total elements minus the derivative of this element times the partial of L with respect to Q at A. Okay, great. Now if you take a look at this equation right over here, right? This is, actually I can pull this out, but actually you know what, I will pull it out. Get it over with. So the derivative of time, I can pull it out, and we're left with QA dot partial of L with respect to QA taken from 1 to n. Oops, lowercase n. Minus. And if you look carefully at this equation right over here, right, this looks like we can, remember, L is a function of Q's and Q dots and time. And if you look at this, right, we can apply the chain rule to this equation right over here, and we can see that this is actually equal to, let me pull out this. So this is A to n of the, I'll make a summation of this. So this is Q at A dot partial of L with respect to Q at A, and then there is a term which is Q at A double dot partial of L with respect to Q at A taken from 1 to n, and that's equal to 0. So if you remember, okay, so this looks like this is the chain rule, right? So remember, this is actually like partial of L. Yeah, it looks okay. And I didn't copy this down properly right over here. And that's supposed to be a second derivative right over here. Oh, and I think I put an extra dot over here and I messed up the equation. Yeah. Anyway, let's put a big parentheses around this. And this is actually, doesn't this look like a chain rule of, so this is your chain rule, right, in the coordinates Q1, Q2, but there's a t missing. So we can rewrite this in saying that this is the derivative of time of the summation of QA partial of L Q dot A minus, and this looks like the total derivative of time L minus the partial of L with respect to time. Oops. So that's these terms right here, these two terms, that's a chain rule. So that's equal to 0. So you notice that there's a summation over here, and there's a derivative on this side, so I'm going to pull out the derivative, and I need to start erasing something, so let me erase the top. So we're left with the derivative of time of the summation of A taken from 1 to n of Q dot A partial of L with respect to Q A dot, and then the minus L. And then there's a minus minus, that becomes a plus, so this becomes a plus. The partial of L with respect to time is equal to 0. And this is what I want to look at. So the question is, if you look at it now, right, so remember, so let me compare it with the other equation for the Lagrange equations of motion. So if Q at A is cyclic, meaning it's missing in, so that Q at A is a generalized coordinate which is missing in the Lagrangian, then we can say that this is 0 because it's missing. There is no QA, and we take a derivative, it's 0. And so that must mean they get a conservation. If QA is cyclic, we get a conservation principle of Q dot A is equal to a constant. Notice now, the reason I did all these calculations, right, well, it's not really long calculation, but whatever, this calculation we just did, right, is QA partial of LQ plus partial, right? So what if you have a missing T? So let me erase this since it's just a derivation. So if you look at this, right, you'll see that if T is missing, so much like a cyclic variable, generalized coordinate, but cyclic corresponds to generalized coordinates, but T is missing in L, this term is 0. If this term is 0, then the derivative of something is equal to 0, which means that this thing is conserved in time. It doesn't change in time, which means that the sum of all the terms from 1 to n, QA, this over here, this quantity, whatever it is, minus L is a constant. This is interesting. So you're saying that if you're missing a generalized coordinate, we're getting a conservation principle that says the partial of L with respect to the partial of the time derivative of the 8th generalized coordinate, right, is a constant. And if T is missing, right, we're getting this quantity called QA dot partial of L, QA dot minus L is equal to a constant. This quantity, right, I'm going to call it H in reference to saying that, and I'll actually give it a name. I'll say this is the Hamiltonian H. I'll just call this the Hamiltonian H function. Notice the H function consists of, it is a function of Q1 to Qn, and it's a function of Q1's dots, Qn. And there might even be a time, but if T is missing, right, of course this will have no T in it, but whatever this is, right, because L is a function of time, so this generalized function called Hamiltonian H, the H function, right, is not be confused. Later I'll call something else called the Hamiltonian with a capital H, right, that'll be in another with its canonical coordinates. We haven't gotten there yet, but we'll call this the Hamiltonian H, the lowercase h. The uppercase h, right, I'm going to refer to as it's a function of variables of generalized coordinates and generalized momenta, which we haven't discussed thus far. Okay, so we're going to get there in a sec. But so let me give this as an example so we can understand what this means. So this is called the Hamiltonian H function, the lowercase h, not the uppercase h. And so let's try this as an example so you understand this idea. So this should be a concept. You should memorize this equation saying that the H function, so you should be memorizing that. So let me erase all this. And okay, so let's imagine that somebody gave you a Lagrangian. Here is your Lagrangian, and I'll assume it's a central force problem. So we have so the Lagrangian consists of, you have some object going around another system, and the distance to the particle from the central force is r, and the angle that it makes is called theta, and blah blah blah. So there's a little mass m, there's a big mass m, and a very small mass lowercase m. And so the kinetic energy of the system, right, T, would correspond to 1/2 the radial coordinates of the system, right, would be r dot squared. The tangential portion, right, would be 1/2 m r theta dot squared. And the potential energy is, for gravitational mass, and I'm assuming m is much larger than the lowercase m. So we don't have to worry about a real two-body system, but to assume that m is much smaller than. So we're looking at a gravitational field, and so if you remember the potential energy of the system, right? As you get closer, as the distance r gets closer, there's a higher potential energy, and because of this, right, we want to make sure this is actually, so the v is after minus minus, so this becomes a plus. So this is actually the Lagrangian for a small mass traveling in a gravitational field around some larger mass some way. So if you look at it, right, we see that, look at this, L is a function of two generalized coordinates, so we're expecting an r theta dot, r dot, theta dot, and t. And if you look carefully, there is no theta missing. So this is a cyclic variable. And so is t. There is no t. No t. So the cyclic variable says that what's being conserved, right, is the partial of L with respect to that theta dot in the cyclic variable. And that's a constant. And so let's calculate that. Okay, so we have 1/2 m r squared theta dot squared. So this is 0, that's 0. So you're left with m r squared theta dot. So whatever this is, right, and if you kind of look at it, right, this actually is the angular momentum. So if you kind of look at it, this is actually the angular momentum. So let's not worry about that, but this is actually angular momentum. So in this system, angular momentum is conserved. So that's a conservation principle. It's a constant. It doesn't change. It's always fixed. Whenever the system is started off initial point and goes around whatever the angular momentum is, it's conserved. But t is missing. Because t is missing, right, we also know that so this is a little more work. So you say the number of coordinates is 1 to 2 of q dot a partial of L with respect to qa dot minus L is a constant because there's a missing t. So let's calculate that. So the first coordinate, right, qa dot, this would be, well, r dot. And the partial of L with respect to r dot, that's equal to mr dot. And then there's the next term, right, which is theta dot. The partial of L with respect to theta dot, we just calculated it, would be, the partial of L is mr squared theta dot. Okay, and then minus 1/2 m r dot squared plus 1/2 m r squared theta dot squared, and plus gm m over r. Oh, didn't match the correct braces type right here, so I'll put this over here so I get a nice braces there. So this is mr squared, so you're left with 1/2 m r dot squared plus 1/2 m r squared theta dot squared, and then there's a minus gm m over r. And this is your h function. So your h function, right, is conserved. So it is a constant of the motion, right, when t is missing. So whenever time t is missing. Now the importance of this equation, right, is that you kind of can see it, right, and I'll just say it ahead of time so you get the idea. This h function, right, when t is missing, right, sometimes, not always, but in this case, right, it definitely is. You'll actually see that this h function, right, is the kinetic energy plus the potential energy, or the total energy of the system. In this case. So you're saying that this h function, right, because it's missing, h function is conserved, and in this special case, right, this h function corresponds to the total energy. So you're saying that missing times in Lagrangian leads to something related to energy, meaning there's conservation of energy if we get a correct way, and I'll explain that in a sec. But generally, the h function is conserved when t is missing. And sometimes, not always, the h function, right, is the energy of the system. Not always, but sometimes. And I'd like to discuss it a little bit more, but I want you to get familiar with the h function. So let me do some more examples on this to make sure you understand. So this means that, so let me make up a weird problem with generalized coordinates. Now the importance of these Hamiltonian, right, is that this Hamiltonian H function and then eventually the capital H function, which is in generalized spatial and menta, is that it leads into concepts of statistical mechanics and quantum mechanics. And so for more theoretical aspects, right, it's actually good to have an understanding of this Hamiltonian because for example, canonical quantization quantum mechanics is based fully on the Hamiltonian. So if you construct the Hamiltonian, we can actually construct the Schrödinger equations of motion from Paul Dirac, and his methodology is called the canonical quantization in quantum mechanics. And all those concepts, right, you'll understand so long as you understand what the Hamiltonian is. So basically, again, so if you have a Lagrangian, and there is a missing t, then this implies that the h function is conserved. And I keep rewriting this, right, because you need to memorize this equation. It's a very important equation. So qa dot partial of L with respect to qa dot minus L. Put a braces on there just to make sure you're understanding. So it is a missing t, and sometimes, right, this h function, this Hamiltonian h, the lowercase h, right, this h function, right, is energy. Not always, but sometimes. And I'd like to discuss that a little bit more, right? But before I do this, let's do an example. So imagine that we have a system, and I calculate the Lagrangian to be and let's leave it at that. So we get three Lagrange equations of motion corresponding to three generalized coordinates, q1. And the first thing you should notice is that if you look at the equation, right, we have that there's a missing q. So let's find the conservation principles thus far, right? So we know that q3 is missing. So it's a cyclic variable. Because it's missing, right, then the partial of the Lagrangian with respect to q3 is a constant. And what is the partial of L with respect to q dot 3? that means it's 2q3 dot is equal to a constant. So this is a conservation principle. So in time, this is being conserved. Nothing changes. This is actually doesn't change for different values of q3. I'm sorry, to this equation for different values of time. But t is missing. So the H function says, right, that is conserved. And so this is really the q1 dot partial of L with respect to q1 dot plus q2 dot plus q3 dot partial of L with respect to q3 dot minus L. Whatever that is, it's being conserved. So let's calculate it. Am I still on the screen? Yeah, still have some space on the screen. That's good. So q1 dot partial of L with respect to q1 dot is 2q1. Okay. So if you're kind of curious, right? Actually, you know what? So I want you to notice that this looks like a kinetic energy term, T, and this looks like a potential energy term, V. Okay, so I want you to notice that, okay? So this is really T minus V, right? So T is this term, V is over here. Let's go calculating this. So Q2 dot, right, is Q2 dot, the partial of L is again 2Q2 dot plus Q3 dot 2Q3 dot, and then there's a minus L corresponding to Q1 dot squared plus Q2 dot squared plus Q3 dot squared minus Q1 Q2. So I'm trying to be explicit about this, but do you notice there's 2Q1 squared, there's a Q1 squared, so we're left with, can you get this on the screen? Yeah, I think so. So Q1 squared plus Q2 dot squared plus Q3 dot squared. Each of the terms cancels, then there's a plus Q1 Q2. But if you think about it, right, that does look like, so whatever happens, this H function has been conserved. And in this special case, Q1 dot squared and Q2 dot squared and Q3 dot squared plus Q1 2 is really T plus V, which is the total energy of the system. In this case, total energy. So this is the total energy of the system. So the H function, right, sometimes is the total energy of the system. Not always, but sometimes. So let me go deeper into this idea of total energy and when is it total energy. So let me erase this and so imagine that we're given a Lagrangian and it has this form of the Q dots. We know that it has kinetic energy, so we're expecting the generalized coordinates to have a Q1 dot and a Q2 dot and a Q3 dot all the way up to Qn. We're expecting those in the velocity terms, right? So, but I rewrite this in terms of saying, okay, let's assume you have a Lagrangian and I have explicitly, right, that some function f1 times q1 dot squared. And then you have a second function f2 q2 dot squared all the way up to a function of qn dot squared. So I'm assuming that where f1 is a function of only q1s and qn, not the dots, no dots, and time. It might even have time. And f2 is similarly a function of the generalized coordinates, including time, but not the q1 dots and qn dots. Q2 dots, and so on. And so we're assuming this. And of course, I'll put a generalized function over here, well, whatever you want to call it actually. Let's say it's W at Q1 to Qn, but it's completely generalized coordinates with time. There might be time in there, but assume that we have a Lagrangian where we can actually have an expansion of some function of Q1 dot squared and Q2 dot squared and dot dot all the way to function of Qn. So an example of this is, so if somebody gave you, actually, you know what, we'll do examples later. And so let's calculate Lagrange equations of motion and see, let's calculate specifically, I'm going to assume that, so let's make it really explicit. Let's assume that there's no t. So there's no t in this equation. So we have a Lagrangian. It's got functions q1 dot squared, functions in front of each of the time derivatives of the generalized coordinates, and generalized function q at n, but there's no time t. Because there's no time t, the h function, right, is conserved. But let's calculate this h function. So we know that this is actually t minus v, and this term right here, right, is your t, the kinetic energy, and I'll assume that this is really, actually, you know what, let's just put minus v because it makes it more explicit. So I'll just put minus v, and I'm assuming that v doesn't have time in it, it's just some generalized coordinates q1 to qn. So let's take a look at this form of this equation and let's calculate the h function. So the h function, right, only in this case where f1 is just purely a function of the generalized coordinates without time, and f2, fn, so whatever that coordinate is. So the h function, right, is going to be equal to f1 dot partial of L with respect to f1 plus f2 dot partial of L with respect to f2 dot dot all the way up to the last term, f dot n partial of L with respect to f dot n minus, and I can just put down t minus v actually, but yeah, I guess I'm going to have to write it out. f1 q1 dot squared plus f2 q2 dot squared dot, and then there's a minus v. So I expanded that out. So that's your kinetic energy term and the potential energy term v. So if you take a look at this partial of L with respect to f1, sorry, this is supposed to be, totally messed that up, didn't I? So that's supposed to be q1, and not f1. So this is q2 dot, and this is q2 dot, and this is, so completely a mistake. Yeah. So anyway, so take the partial of this, dots, let's not forget, partial of L with respect to q1, so we're left with, so we'll get f1 q1 with respect to, so there'll be a 2 coming out, q dot q1 squared, so we'll get 2f1 q1 dot squared. The next term will be 2f2, so I'm kind of skipping a couple steps, just doing it in the head, so I don't want to waste time doing this. q2 dot squared plus all the other terms that correspond to this, minus f1 q1 dot squared plus f2 q2 dot squared plus dot minus v. And if you look, each of these terms cancels the 2, so this term cancels this 2 and stuff, minus, and then the plus v. So we're left with f1 q1 dot squared plus f2 q2 dot squared plus dot all the way up to v, which is the kinetic energy T plus v. This is interesting because what you're saying is that if you get a Lagrangian where the time derivatives are in quadratic terms with functions in front of leading terms, right? And they're all separable like this, right? f1 q1 dot squared, q2 dot squared, and f2 and so on. In this form, right? Then this h function is the total energy of the system. So this is important, meaning that, so if you look at the Lagrangian I did earlier, right, for the central force problem, right? So if you kind of remember what Lagrangian was, it was supposed to be the radial was 1/2 lowercase m r dot squared, then the tangential portion, right, was 1/2 m r theta dot squared, and then there's the central potential. So we have a large mass with a really small mass approximation. So if this is your Lagrangian, right, you can automatically see that. So let me write this in explicit details. So this is r dot squared plus 1/2 m r squared theta dot squared plus gm m over r. Notice that this term is the minus v and this term is the t, but the kinetic energy, right, has terms which has factors, right, which are basically your F1 and this is your F2. So you have terms, right, which don't have any derivatives in them. So functions of R1 and theta, R1 and theta. And so when you look at it, it has this form. And since it has this form, right, the H function is the total energy of the system. And since it doesn't have any time at t in it, it's conserved. It's a constant of motion. So it's very specific. So there's only specific Lagrangians, right? Not every Lagrangian, right, will have conserved energy. But some Lagrangians, when they have this form, right, and they're missing t, right, that energy is conserved, and it is energy. That H function is the total energy. So it's a very important idea that if you have a Lagrangian, right, and this Lagrangian, right, actually minus v. Oh, it's a little noisy today. So let me erase this, right? Okay, so now let's go into our concept of the Hamiltonian. Actually, this video has gotten a little bit longer than I expected, so I'll actually make another video on this because it's already up to 42 minutes. Anyway, so this leads us to the Hamiltonian H function, and so conservation of energy, and yeah, so if the Lagrangian has a certain form in quadratic terms in the dot product, right, in the time derivatives, right, then things are conserved. Then the H function is energy, and energy is conserved. Yeah.